In this session, we've got a variety of different topics, and we're going to be starting talking about securing IPv6 neighbor discovery. And we've got Thomas Scheffler all the way from Berlin to talk about his work.
Hello. So this is better. Hello, everybody. I'm Thomas Scheffler. I'm here from Germany, Berlin, and I'm going to present you some student work which we had done in collaboration with the University of Potsdam. And what we were looking at was how can we secure, or is there a different way to secure neighbor discovery in access networks than what had been proposed previously and what is being implemented or proposed in several other aspects. And we are actually trying to work this out by using an SDN approach, where we actually build an application which collects all the neighbor discovery messages from the network. So this is the outline of the talk. Well, actually, many of the comments I got from the reviews actually triggered me to go a little bit back in history and talk about what neighbor discovery and ICMP issues actually are, and how they can be exploited. And then I'll focus on what we did. So IPv6 is kind of still the new protocol, 20 years old now, and ICMP is one of the big changes in the protocol in regards to what had been there in IPv4, and which is now maybe different from what we had before. So we can do stateless auto configuration and router discovery. We have a different address resolution process than we had in IPv4, and we now have all kinds of other options which we have in order to do something like multicast discovery, etc. So all these changes actually led to a fairly new protocol, or fairly different protocol from what we had in IPv4, and this actually sort of now opens up several possibilities to actually exploit these kind of things. And maybe the most obvious change was actually the address auto-configuration, which changed the way IP addresses are assigned to hosts. I mean, we now have DHCP in all the networks, so for the end user may not feel so different from the end user perspective, but at least the protocols are very, very different. So the assumption in IPv6 is basically that you do some sort of address auto-configuration, and even if you are going to use IP, if you're going to use DHCP, it's actually sort of still rely on some of the mechanisms here. So by default, all the hosts do stateless address auto-configuration, and in order to configure address, there's a way to maybe take some data from an identifier like a MAC address and make this into a valid IPv6 address. And what you then do is you do a so-called duplicate address detection, which lets you know that this address is actually unique on the network. And as I said, you can also use DHCP-v6, but not as widespread as it is in IPv4, and a lot of people don't ever actually implement it, and even if you implement it, it means that you still have to do some of the first steps in the auto-configuration process. So how does this actually work? So basically what you do is you have IPv6 addresses now have something called a lifetime, which may surprise people that you have actually now sort of tentative addresses and preferred addresses and expired addresses. And when you do generate a new address, you actually set it into in the state of being tentative, and you need to make sure through the process of duplicate address detection that this address is actually being unique on the network and you can actually use it. So how does this work? You send off a neighbor solicitation message to the network where you set your source address to the unspecified address, and then this gets sent out to the local network, and you don't ever expect to get a response back from this, because sort of that's your way to say, oh, you're assured that this address is actually unique on the network. So that's how it should work. That's how most of the times what you see on the network. But it's actually now possible to attack these kind of protocols, and it's very, very easy to do this. So and you can actually DOS somebody just by replying to these kind of messages on the network, and other attacks are possible as well. So how does this DOS thing actually work? So somebody just sort of some prankster or some attacker actually sort of just monitors what's going on, what's being sent out to the network, and then just replies to this. And what happens then is that your host says, "Oh, sorry, I just got an answer back. I can't use this address." And it may pick another one depending on the implementation, but then again, you do the same thing again and again, and you actually DOS the host from actually being active on the network. That's just one example of what can happen in IPv6 neighbor discovery. So there's other attacks as well. So what did people think about it? So they said, oh, well, we have this nice thing called IPsec, so we just secure all our neighbor messages or neighbor protocol messages with IPsec, and then so the problem is solved. The trouble with this is this doesn't really work, because in order to set up a security association, you somehow have to have a valid IP address, which you don't have because you're in the process of configuring one. So this would actually require that you have previously configured manual security association on your devices in order to join the network. So kind of a chicken and egg problem here. Then people realized that we need something else, and they developed the secure neighbor discovery protocol, which is a nice idea. I like it very much. Unfortunately, nobody sort of either implemented it, or even if they implemented it, we found that there are some potential vulnerabilities against it. Just by sending arbitrary messages, you can actually cause a resource exhaustion attack. And so I think that's probably the point where people said, oh, don't bother with that anymore, and we don't implement it. So how do we actually, we as our research group actually cut to this? We sort of monitored all these activities very closely in the time frame from 15 years ago or something like this, and we actually found, and that's, I don't know if it's known by everybody, there's actually good attack toolkit out there. So if you ever wanted to play with this yourself and find out what's possible on these protocols and what kind of attacks are there, there's actually the THC toolkit here. So it's actually being developed by a guy in Berlin as well. So I met this guy. He's a very, very nice guy, but sort of very interested in how to break IPv6. People came up with all kinds of changes to the protocols. We now implemented something like router advertisement guards and silicon on your access switches, etc. So kind of the problems seem to come or gone out of focus, and nobody really cares anymore. What we did is in a couple of years ago, we started looking at IPv6 support in IDSs, and specifically in Snort. And the developers there said, yes, we are IPv6 compatible, but this meant they were only looking at layer 3 and not looking at specific protocols. They didn't even have a way to distinguish an IPv6 ICMP message from an IPv4 ICMP message. So we did some implementations there to allow this distinction. And so we looked at some of this in order to detect NEP attacks in IDSs, but then found that maybe one way to do it, but there's maybe others. And instead of using IDSs, we could actually use an SDN switch to do fairly much of the same thing. So we could monitor links and monitor what's going on the link. And potentially this is also cheaper to deploy and maintain. But once we do this, we can actually go a little bit further and say, oh, well, now we can also filter, not only monitor, we can also put stuff on the network, on the SDN controller, which allows us to give more control over what's actually going on in the network. So we built an NDP proxy, or an intelligent selective proxy. It's not discriminatively proxying messages. It just does this if there's a certain data model met. We implement this in the RIO framework in Python. And what we do is we monitor the network, and whenever we see a duplicate address detection message, then we take this as the authentication hook for our data model. So this generates a host cache entry in our controller, and this allows us then to sort of distinguish between what we should forward or drop on our networks. Other than this acts as just as a normal MAC router switch for IPv4, and we additionally also implemented the router advertisement guard. So actually our controller is the one who is sending out router advertisements, and if somebody else does, then we just block this. What we also did is we didn't want to have every kind of traffic or all the NDP traffic hitting the controller, because this would potentially cause some performance issues. So we managed this by using different priorities for our flow rules. So we have a catch-all rule, which has the lowest priority. If somebody is known, a MAC is known, we have these flows to take a priority over them. Then we filter IPv6 messages and such, and then we have NDP traffic, which we catch. And if we know this guy, then sort of this flow rule is actually taking priority over this. So we should only ever see the first NDP package for a certain flow, and then all the subsequent messages should be switched directly from on the switch. So the idea was to have this deployed so that we don't need to change any kind of anything in the implementations or in the protocols, and have this running. So here you see a big picture of our architecture. I'm not going too much into this. Just some particularly of Rio is actually this. We needed to. Well, we only have a single thread running, so we need to make this so that it's actually something of this is going to be called in parallel. So how do we learn the host on the network? So we, as I said, we use the duplicate address detection messages whenever we see somebody using an unspecified source address. Then we take this as a hint that that might be a new host on the network. And whenever we see a second one, then we block this. This could lead potentially to the case that if somebody is moving from one port to the other with his machine, that he is himself blocking himself. But we just take this chance, and sort of after a certain configurable time period, we actually drop these entries from the cache. So it shouldn't be blocked forever. It shouldn't be just blocked for a certain specific time period. So, and then sort of if we have our cache built, our neighbor cache, then we use this neighbor cache here in order to validate packets going between these entities. And whenever we have a full active communication going on between some entities, then we actually install flow in the SDN switch. So, and regular traffic should be actually also being able to cause these flow entries. And the idea is that when we have some bidirectional communication going on, we actually have these going over the flows, and we implement it as such that sort of whenever there's a new packet being triggered, then we have a timeout period for the flow rules, and they should stay active as long as there is active communication between the networks, or between the entities on the network. So after a certain time period, these flow rules may time out if somebody is failing to send any new traffic, or if somebody is maybe being removed from the network. We not immediately remove these, we remove the flow rules from the switch, but we not immediately remove the host cache entries. They will get purged after a certain time period, but this is for longer than it is usually for the idle timeout on the flow rule. So we tested this in basically a lot of it in Mininet, but also some of it on some real OpenFlow hardware. So the basic functionality of onboarding IPv6 hosts is quite easy to implement and works as intended. The main challenge really is in maintaining this host cache, because we can't guarantee that we see all the packets going on in the network, and we can't. I mean, the challenging bit is if you have some host maybe shutting down or maybe going to sleep and not answering our probe packets when we're trying to figure out if this host is still active on the network. We also did test some performance issues with this, because sort of basically now we are in the packet path, and whenever we need to process something, then it potentially takes some time. And we found out that it takes some time, which is mainly due to the fact that we have a non-optimized host cache data structure. The trouble here is that the normal MAC learning switch can just sort of key on the MAC address. Here we now have to check MAC address against different and potentially multiple IPv6 addresses. So we have to go through the whole cache, and this is done in Python. So it's not yet production ready, but sort of that's. But these times are only true, or these times here in milliseconds are for just the first ICMP packet being processed by the switch. Whenever we get these things, the flows installed, then all subsequent packets will be switched much more faster. So what's our current limitations? Our model sort of assumes that we have one host per switchboard, that all our hosts actually doing duplicate address detection, and the controller sees all these messages, and currently it only works with a single switch network, which need to be extended. But sort of the main challenge, as I already hinted, is really what happens if a host is hibernating, sleeping, or if hosts may change their MAC addresses while they are working on it. So that's actually something. What we found is that sort of it's actually we feel is a very good idea to use SDN to do this kind of things. The trouble is that sort of as Ethernet and IP are not very, very well integrated with each other. So maybe it's time to change something like this, that we say, oh, well, yes, an Ethernet switch isn't supposed to be a layer 2 device, but it never really was a pure layer 2 device. So there's still some interaction between these layers, and maybe it's time to get these a bit more integrated in order to also assure some security and reliability in the networks. And we see this already being implemented in something like Wi-Fi managed Wi-Fi networks, where you have the same or similar situation. And here we have mostly proprietary controller models, and I would rather love to have something which is more open and more standardized, so that we can actually use it in whatever we want to do it. So yeah, the thing is, we want to like to support extend our work to work with multiple switches, and maybe use a different framework, maybe move away from OpenFlow and use P4, but that's still not yet decided. So if you want to have a look at our code, it's here right on the slide. So you can go to a Git repository where you can download this stuff. And if you want to contact me, here are my contact details. So if there are any questions, I'm happy to answer them.
Let's thank the presenter. So we probably have time for one quick question while the next presenter sets up.
I'm curious whether does your code assume no packet loss for the DAD packets?
Yeah, basically.
You're going to have a bad time. Okay.
Yeah.
Well, I see. Yeah, because also there's, I've seen people do that in production implementations, and it's fallen over for them. Because, for example, I mean, if you're on wired, maybe you're okay.
Yeah,
But if
the target is wired networks. So yeah.
Because if you're on Wi-Fi, like.
No, we're actually actively targeting wired networks because I feel like that's a neglected area. So nobody really does this. For access networks, I don't see anybody doing it. I mean, we see a lot of activities in the data centers. We do see a lot of activity in the Wi-Fi space, but for just ordinary switched Ethernet networks, everybody assumes it's just there. You're right. I mean, there's a whole lot of assumption here, and the question is really, should we maybe change some of the assumptions because this transparent switching approach for Ethernet has its merits. It's working, but it's also introducing a lot of troubles which we may not have if we had a much better integration on finding out who we actually are, and basically using that as basically just sort of our that's the only thing we could use without changing any protocols.
Cool. I guess you guys can maybe chat more on the break. Thanks for your talk. So up next we have Sylvester Nadas from Ericsson Research. He says he's been working with traffic management for 20 years, and he's interested in finding practical scenarios where fast and precise control of resource sharing is needed among a high number of flows. So I think if you've got practical problems like that, perhaps find him in the break. Let's thank our speaker.
Hello, everyone. Can you hear me well? Yeah, take it as yes. So I'm Sylvester, presenting our paper towards core stateless fairness and multiple timescales. It's a paper together with my university colleagues. You can find all our papers on our homepage. So our goal is to extend fairness to multiple timescales. So first of all, we want to define some kind of multi-timescale fairness. We want to build on existing frameworks, namely two frameworks. One is the per packet value-based core stateless framework. The other is another paper of mine, not with the same authors. It is called multi-timescale bandwidth profile. And we also want to provide efficient and versatile implementation. And versatile meaning that we want to provide fine-grained fairness on multiple timescales that is independent of traffic mixes and resource bandwidth. And I also want to demonstrate some advantages. And some motivation for this, as an example, motivation is from a paper, getting a scheme to instantly serve web flows for improved performance while maintaining fairness between other persistent flows remains an open and significant design problem to be investigated. And we think that we take a step forward in that direction. Sorry. So overview of core stateless resource sharing with the example of per packet value-based core stateless resource sharing. It's a framework which allows a wide variety of detailed and flexible policies. I will go to some of the details of these policies, and enforces the policies for all traffic mixes and scales well with the number of flows. There are two components, packet marking at the edge and resource node everywhere else, mainly in the core, which does AQM and scheduling. So packet marking at the edge encodes the policies into a value marked on each and every packet. And there is a packet marker per flow being the unit where we have resource sharing policies. And based on that packet marking, the resource node doesn't know about policies, flows. It doesn't have to have separate queues. It only does its behavior based on packet marking and packet marking only. And we have very fast and simple implementations. We actually had a paper 1 year and 2 years ago at INRW about these resource node implementations. But this paper is not about resource node implementation, and we will, in this paper, use our resource node implementation from last year. So bitrate measurement and timescale. So bitrate is a derived measure. there are only discrete packet arrivals, and these can be translated to bitrate, and bitrate always has a timescale associated. So it's some kind of volume divided by some kind of time. And there are some natural timescales like RTT, 1 second, session duration, maybe 1 minute, 10 minutes, and for example, monthly cap is also a kind of like a bitrate limit over the month. So you can see that some examples for the packet arrivals. So if in an RTT more packet arrives, then the RTT bitrate will be larger. There can be a session bitrate. There can be bitrates averaged over periods which are larger than a session, and then these bitrates will be smaller than the session bitrate. So why does that make sense? Sorry. That makes sense because we can have fairness on multiple timescales. So when do we measure bitrate? We can measure bitrate only when the source is active to describe, for example, the performance of the source. But we can also measure bitrate during both active and inactive period to judge fairness of resource sharing. So what can be a fairness goal on multiple timescale is to balance the bitrate measurements among these multiple timescales, and for example, to allow higher share on shorter timescales for flows below their fair share on longer timescales. So there's an example there. If we have the same fairness on each and every timescale, 1-to-1 sharing, then there is the blue flow, and blue flow is having the same resource share like the yellow, and it takes quite an amount of time to download that blue flow. But if you take into account that on a longer timescale, the blue flow didn't have any transmission, you can allow a higher share on the shortest timescale. So you can allow this 1-to-5 share on a shorter timescale, and still on the longer timescale, the resource sharing remains 1-to-1. And assuming that the yellow user is downloading alone, so the yellow user's download time won't change, while the blue user's throughput will be improved quite much. And there is one more thing. This was true for our previous paper, but we also aim at smooth transition at relations between the rates measured at different timescales. So we don't want to have sudden rate changes when the relation between rates changes. I will go to more of the details later. There are much more novelties compared to the previous paper. But first, a short introduction to the pair packet value marking, like versatility. So we define, in the pair packet value framework, we define policies through throughput value functions. And these are for a single timescale. They provide a very fine gain control, which is independent of traffic mix and resource bandwidth. So these meet our requirements for a single timescale. And if you have a traffic mix, if you have a resource bandwidth, then that will always result in something we call congestion threshold value. And congestion threshold value is a horizontal line on this throughput value function curves. And if you take the intersection of the throughput value functions and the congestion threshold values, then you will get the throughput targets at all of the congestion levels. I have 3 examples here: high congestion, medium congestion, low congestion. And in high congestion, there are several traffic classes here, but the interesting ones are the gold and the silver. So in case of high congestion, we would like gold flows to get twice the throughput of silver flows. In case of low congestion, we would like to have gold flows get 4 times the throughput. So, and what is in between is medium congestion. When silver flows already reach 10 megabits per second, then gold flows can't just get the 4 times, but it gets the rest. So it gets something between 2 times and 4 times. So the rationale behind is to have some kind of, for example, minimum throughput target, and until the minimum throughput target is met for the lower priority flow, we shouldn't prioritize the higher priority flow that much. And this is, again, an illustration of the versatile policies we can have with this framework. And again, we just set, based on these curves, we define packet marking. So how can we have packet marking based on a throughput value curve? We have incoming packets, we measure the rate somehow. So these are the rate-based packet marking policies. So we measure, for example, rate 48, and then we determine a uniform random rate between 0 and that rate, take the value of the throughput value function at that point, and mark that packet value on the packet. And just by having that marking and maximizing the transmitted packet value in the core, we will realize the resource sharing targets on this. So there are other papers about how this happens, but it's important to understand this kind of thing for understanding this paper. So, but for this, we need a single rate measurement, a single timescale. But if we want to have multiple timescales, we need to measure bit rates on multiple timescales. And we actually introduced two different rate measurement algorithms. We have token bucket-based rate measurement algorithm for the RTT timescale only, because we think that the token bucket-based rate measurement models the fast throughput and buffer share of the bottleneck quite well. It's a single token bucket. Its rate changes when the bucket becomes empty or full. Details are in the paper. And the other rate measurement we use for the longer timescales is a sliding window-based rate measurement. So the rate is basically the amount of bits arrived in the last timescale interval divided by the length of the timescale, and it's actually an efficient approximation of that algorithm, TDRM TVMA. And then interesting thing is about this rate measurement algorithms, if you think about them, is that when transmission starts, if you order the timescales increasing and have the rate measurement algorithms, when the transmission starts, then the bit rate on the smallest timescale is always larger than the bit rate on the next timescale, and so on. So you can see an example there, like timescale 1 sec, 5 sec, 10 sec. And first, the 1 second rate measurement reaches the maximum throughput, then the 5 second, then the 10 seconds, and it's vice versa when the rate decreases or the transmission stops. So for new flows arriving to the system, they will have pretty big bit rate measurements on low timescales, but they will still have moderate rate measurements on longer timescales. So how can we then define throughput on multiple timescales? Instead of having a single throughput value function per flow type, we introduce one throughput value function per timescale per flow type. So for a single kind of flow, instead of having one such function, we are having 4 such functions, and all of these have a timescale associated. So what does it mean? We first define dominant timescale. So dominant timescale is when, for example, timescale R is the dominant when the rate measurement on that timescale is the largest. And if there are more than one, then the longest timescale applies. And as an example, have two flows of the same flow type. One has dominant timescale 1, the other dominant timescale 4. So one has just arrived, the other has a long history in the system. And we say that multi-timescale resource sharing is such that they should share the bottleneck according to TVF4 and TVF1. So it is as if they would be different flow types in the single timescale framework. So if you look at it, then the new flow is the blue one. It should have much higher throughput share than the old flow, the green one. But we also aim smooth transitions when the relation between R is changed. So if there is an oscillation between which is the dominant timescale, we don't want to have an oscillation in the resource sharing. So how we achieve it? There is something in our previous paper called multi-timescale bandwidth profile. And it has a few drop precedences and a few token buckets associated with each of these drop precedences. And it can mark the given drop precedence if there are enough tokens in all of these buckets. And in theory, we could quantize multi-timescale throughput value function to an MTS BVP, but it's not practical because we would have thousands of token buckets. But we can use that to approximate what happens. So we can look at multi-timescale bandwidth profile as an indirect measurement of rate on each timescale. And limiting token buckets would determine the measurements. Again, I can go to all of the details there. But if you look at what happens is that the transition between the throughput value function will happen at the rate measurements at the different timescales. And by using that, we can have an efficient packet marking based on these throughput value functions. So you can measure bit rate for all of the timescales. At these bit rates, you can determine the distance between the throughput value function, and that will result the blue region of different throughput value functions. And similarly to the single timescale algorithm, you can have a uniform random number, determine the right region for determining your packet value. So you can choose between region 1, 2, 3, and 4 based on the relations between your random number and the measured bit rates, and determine your packet value accordingly. And it's actually a pretty fast algorithm. So what can we achieve with this? We did some simulations to understand what happens in the system. It's a pretty complex system. Can we achieve some kind of gains? Can we indeed boost new flows, things like that? So we use an S3. We use the same core scheduler like in our previous argument with 10-millisecond delay target. We had several flows. One flow consists of either a single DC TCP connection or four cubic TCP connections, which means faster slow start for the cubic flows. We have 10 millisecond, 1 second, 5 seconds, and 10 seconds as time scales. And TVF4 was gold and silver, as in the single timescale TVF. And in each and every timescale, we doubled the share. So on timescale 1, we should have twice the share. Timescale 5, we should have double the share. Timescale 1, 4 times the share. And timescale 10 millisecond, 8 times the share of the long time 10-second average throughput. So some simulation scenarios. We had first greedy flows of the same traffic class and DC TCP. The blue flow was in the system for longer time than the longest time scale, and then the yellow flow arrives to the system. The left-hand side curve is with the multi-time scale PPV, and the right-hand side curve is the reference. So in the reference, you can see that with the old framework, we knew it converges to the fair share pretty fast. We have 1 second average throughput here, so it's basically converges within 1 second. But what happens with the multi-time scale is that when a new flow arrives, it is boosted first, then there are some oscillations, and then they converge to the fair share. And how can we visualize it or understand it even more is to measure two things. One is we call the flow time average, and there is the 5 second time window average. So the flow time average is the total amount of bytes the flow has downloaded divided by the total amount of time the flow has spent in the system. While the 5 second time window average is basically looking back at the last 5 seconds and see what was the average throughput there, including periods when the flow wasn't even there. And what you can see, I highlighted some cases with the cubic multi-time scale versus the reference. So what you can see there is that the flow time average, this is a relative curve, and one is the equal share. It's not anymore the fair share. So the flow time average has a high boost at the beginning, and actually the 5 second average fair share of the flow reaches almost the equal share in 1 second, which means that in 1 second, the flow can download as much data as his equal share in the last 5 seconds, including the 4 seconds when he wasn't yet there. But after a period, you can see that it will go to the equal sharing. So it will converge to equal sharing with flow. So if a flow is in the system for a long time, it will have equal share with other flows. Maybe I will show this slide first. So in this example, there are continuous arrivals. 10 new flows arrive to the system every 10 seconds. And you can see that the number of flows is of course increases, so the per flow equal bandwidth decreases. But for each of the new flows, they are temporarily boosted, each and every case, independently of the number of flows. And then they all converge to the equal share as we desired. And there is another example here. This is a very simple adaptive streaming model. It inserts some kind of download to the system every 10 seconds. And there is an initial time, an initial download, and we show how much time does it take to download 1 second worth of video data. And because the MTS, the multi-time scale resource sharing, boosts the initial part, there is a much faster startup. So the time to play is much less. And also, every time it feels, yes, it's basically the last but one slide. So, and it also feels the player buffer much faster. So it defines and implements multi-time scale fairness for on-off flows also. So can I say this? Yeah. Okay. So this initial results look really promising. So we have some kind of multi-time scale fairness which works. There are significant performance gains, so advantage for new flows for the starting phase. And there is also better long-time fairness for flows with on-off behavior. But there is quite amount of future work. We are not quite sure how it can be used, how is it useful. So what is the for example, what is the practical number of timescales to be used to reach real advantages for the users? How shall these be dimensioned? How shall we design the multi-timescale throughput value functions? We use the simplest example we can imagine. Does it make sense to use different kind of policies in this TVS for various timescales? And what we can find which can be relevant like further. So, thank you.
Well, thank you, presenter. Okay, so we're still running a little bit behind, but we've got time for one question. Questions? I guess I'll ask one quick one. So are you thinking about this mainly in the context of like data center networks and data center workloads, or would you see it in other types of networks?
Our main focus is really access network and broadband and users. So it's not in data center. It's more about smaller, even smaller timescales. But it's, for example, for residential access and fare sharing over congested access links, or mobile and such.
Awesome. All right. Let's thank the presenter one last time. Next presenter is remote. All right, Satya, are you there? Can you unmute yourself?
Hey, yeah, I'm here. Can you hear me?
Okay. Yeah. Yeah, and we can see you too. Okay, so you're just going to have to let me know when to advance the slides. So for our last talk, we've got Satya Kumaran Mani from University of Wisconsin, and he's going to be presenting some work on managing time in the internet.
Hello, everyone. I'm Satya. I'm from the University of Wisconsin-Madison. And thanks to visa processing delays, I'm currently in Central Daylight Time, which is an hour behind Montreal. And today I'm going to be talking about our work in examining how current local time is reported by devices on the internet. Next slide, please. Can you go to the next slide, please?
Oh, sorry.
I think you skipped a slide. Yeah. So internet time synchronization is useful for a variety of applications. And these mechanisms synchronize clocks on devices to a common timescale such as UTC. To make time more comprehensible, people-facing applications need to translate time from UTC to current local time. And writing code to do this translation is notoriously difficult because several factors such as the daylight saving time rules and changes to these rules need to be considered. Further, several edge cases need to be handled as well. For example, the island nation of Samoa skipped an entire day in December 2011 because they wanted to be on the same time as Australia, their closest trading partner on the other side of the international date line. Next slide, please. So time zones originally originated in the late 19th century in order to improve coordination in railway and telegraph networks. And the daylight saving time was introduced in 1918 in the US in hopes of saving energy during the First World War. And modern applications such as calendars need to handle and know about time zones. And the time zone database is a critical asset that contains data and code that helps applications do this handling. And this database was created by Arthur David Olson in the early 1980s. Next slide, please. So this time zone database consists of definition of time zones and the daylight saving time rules for every time zone. And it contains both historical and current data. So in this small snippet we have here, we have both the definition of a time zone and also definition of DST rules. So we've skipped a few lines here to save space and time. So on top, we have the time zone definition for the New York time zone. And it says until 1883, New York was behind GMT by 4 hours and 56 minutes and did not follow any daylight saving time. And until 1967, New York was behind GMT by 5 hours and had its own rules for observing daylight saving times. And right now, the daylight saving time in New York is same as the rest of the US. And below that, we have the DST rules currently in effect in the US from 2007. The rule says that daylight savings start in March on the second Sunday, where clocks are advanced by 1 hour, and end in November on the first Sunday. So information like this is organized as text files in typical unique style and bundled with code and reference implementations for C API functions to handle time zones and utility programs in the database. Next slide, please. So this database was placed in the public domain by Olsen in 2009, and hence this is not owned by any entity. The database is currently hosted by IANA, and the process to update the database is defined in RFC 6557. So the database is maintained by a community of volunteers, and all decisions are finalized and published by a primary maintainer. The current primary maintainer for the database is Paul Leggett of UCLA. The current version of this database has 348 time zone records for various time zones across the internet, across the world. And this database is used by almost all major operating systems, such as various flavors of Linux, Android, iOS, and various programming libraries such as PyTZ and JoraTime, etc. Next slide, please. So the actual rules for the time zones and observing daylight saving time is decided by the corresponding local government authorities, and this information and changes to such rules are published either officially or through the media. And when such changes or updates are known, the time zone database community discusses such changes in the official time zone mailing list. And once the changes are finalized, a new release is prepared by the maintainer and published at a known location. Then it is up to the consumers of this database to push these updates to their end users, which are typically done through operating system updates. And any delay in this process has the potential to cause major disruptions. For example, in 2015, due to ongoing elections, the government of Turkey decided to delay the end of daylight saving time and announced this change only 3 weeks in advance to the actual date of effect. So what finally happened is the update to the database being pushed was delayed, and the iOS update bundling these changes reached the end users only 3 days before the date of change. So what happened was a huge confusion on what time of day it is. So given the wide use of the database and the huge impact the update process has, we are motivated to understand the evolution of the database and the update and maintenance processes. Next slide, please. Yeah, and for this analysis, we use source files from all 240 releases of the database that span over 26 years. We also download the entire mailing list archive and perform text search on the archive to identify problems and anomalies with the database, which we'll later discuss in this talk. To perform this analysis, we built a Python-based processor tool that can compare consecutive releases to detect effective changes in zone and DST rules, And this tool is also capable of identifying correction updates, that is, updates that make changes to previous updates. So in total, this tool identifies about 2,200 updates to zone and DST rules, with 400 of those labeled as correction updates. Next slide, please. So based on this tool, what we do is we take these updates and then classify them into either making changes to time zones or to DST rules. And since we can extract the release dates of this updates from the mailing list, we also see whether these updates make changes to timestamps in the past or in the future. And from the charts on the right, we can see that the majority of the updates have to deal with the DST rules. So this shows the huge impact daylight saving time has on managing time on the internet. And also, an interesting fact is, even though the database does not make any claims for the accuracy of historic data before 1970, a majority of the effort goes into improving the historical accuracy of the database. And since we can also extract the release dates of these updates, we assess the timeliness of these updates. And from our assessment, we see that about 80% of the updates are published within 100 days from their actual date of effect. And of that, 20% of the updates are published within 15 days or less from their date of effect. Next slide, please. Then we also look at the community by assessing the mailing list archives. And we see that over the span of 30 years, we have about 19,000 emails in total from 1,800 unique contributors. From the histogram on the right, we see an increasing trend in the number of emails and contributors after 2012, particularly after the adoption by IANA. And this trend is correlated with an increasing use of the database, particularly after the adoption of mobile and smart devices. Ingesting information from such a large number of contributors is a potential concern from a management perspective. Next slide, please. So earlier we saw that most of the updates deal with DST rule changes. So then we wanted to reason about these changes. Why do we see so many changes in DST rules? Our hypothesis is that DST rules are often, the changes to DST rules are often administrative reasons that are correlated with major events such as wars, policy changes, or major gaming events, etc. To evaluate this hypothesis, we analyze the, so to evaluate this hypothesis, we take the most recent version of the database and count the number of updates made to each time zone or DST rule. We generate a histogram of these changes, which are made by the government entities. And then we group these time zones by country. And then we look at the history of the country in question. So in this example shown here, so we see the histogram of rule changes for North America. And as we hypothesized, after eliminating all noise, we see that huge number of changes correspond to major events such as the World War and policy updates such as the Uniform Time Act or the oil embargo that was in effect during the energy crisis in the US. So in addition to proving our hypothesis, this also shows that the time zone database provides a unique perspective on world historical events. We see similar results from time zones belonging to other countries, which is not shown here for space constraints. Next slide, please. So next, we try to identify the problems and anomalies that are related to the database updates. Our intention here is to highlight the importance and the impact of these database updates. So as mentioned earlier, about 19% of the updates are flagged as correction updates by our tool. So these are updates that make changes to previous updates. And we see that most of these corrections arise due to incomplete information being released by authorities, such as authorities just announcing the start of a new DST policy without an end date, which later need to be updated. But some of these correction updates also are related to errors that are actually made in the database. These errors highlight the problems in the informal update process that has to ingest data from a large number of contributors. And sometimes we see that even correct database updates making unintended or causing unintended bugs in other software systems. For example, a provision to include a negative time offset in the database broke several software systems such as OpenJDK, the Qt framework, etc. Another issue that we notice in the database updates is the disruptions caused by delayed updates, which we saw earlier. Next slide, please. So based on our analysis, we have come up with a set of recommendations which are intended to improve the security and integrity of the overall system. Our intention here is not to impugn any individuals who have indeed contributed significant time and energy in the upkeep of the database. Rather, our goal here is to expand perspectives and to start discussions about this critical asset. And as such, we do not provide any implementation for a recommendation because these recommendations could be implemented using standard open source tools. And our recommendations are intentionally high level. We believe that the details should be fleshed out within the TZDB community. Next slide, please. So our first recommendation is to codify the overall update process by introducing more formalization, such as standard release tools, standard documentation, a ticketing system to track each and every update, and most importantly, a test suite to ensure correctness of the database. We recommend that these updates are treated in the same vein as Linux kernel patches. And then the overall update process is extensively relies on the primary maintainer or coordinator of the database. So for a motivated attacker or a government entity, it might be possible to introduce unwanted updates into the database through impersonation of the contributor or the primary maintainer. So we recommend stronger cryptographic measures to improve security. And we also believe that introducing more formalization would also help in this regard by introducing more transparency. And finally, we also recommend an independent third-party audit of this database, which could be conducted periodically and could test the database from the perspective of end users from different time zones. Next slide, please. So in summary, we examine how the time zone database is used by devices connected on the internet and how it has evolved. We also look at the maintenance and the update processes, and we see that daylight saving time has a huge impact on the update process. And we also see a huge amount of effort going into maintaining the historical accuracy of the database. Based on our observations, we come up with a set of proposals that will aimed at enhancing the security and integrity of the database. Our goal here is to draw more attention and resources towards improving this critical asset. Next slide, please. Thank you.
All right, let's thank the presenter. So we probably have time for a question.
Hello. You mentioned the necessity of having safeguards against malicious updates of the database. You mentioned that there were a lot of changes that were actually fixes for previous changes. But did you notice any actual malicious update in the last 26 years? Did it already happen?
No. So we have not seen any malicious updates, but we've seen errors that were caused or errors that were unintentionally caused. But we do believe there is a weak link, and this could potentially be exploited by malicious actors.
Yeah, my concern was that it may not be necessary to add new process, new rules, new security for something that may never happen.
But we do believe there is a possibility for an attack due to the informal update process that is involved. And as we've seen, any delay or unintended entry could cause mass confusion due to the uncertainty of time. So this could potentially be used by any malicious actor.
Hi, Neil Jenkins. You recommended introducing tests. As this is data, not code, what are you testing and how are you going to
So
validate
the database actually contains data and also code. So there is this compiler that compiles all this data to binary files that are later used by system utilities. So tests could test that code, and also it could test the validity of the entries itself.
Sure, but the whole point of this talk was on the data, not the
That's-
code, which is just an
true.
example code base anyway. Just the data that
That's
we're
true.
concerned about being incorrect.
Yeah.
Is that correct? So that's not
Right.
part of these
So
tests,
yeah, finally, what this data accomplishes is for every time zone, it gives you the effective offset from UTC. So the tests could actually make sure all these offsets are indeed correct. So that could be
How? Because the whole point is this is the database of what
Right.
those offsets are. So what are you testing against? Check.
right.
where,
So some of the time zones could be selected where the test could manually check for offsets. We could the test could pick certain time zones, for example, the Central Daylight Time, where the offset is well known, and then make sure the data is indeed consistent with that. So randomly, time zones across the world can be picked and then could be checked for consistency.
So your test is a separate database of time zone data, of which you test your time zone database against.
Yeah, maybe in a limited scenario.
Okay.
I guess one last quick question.
Janayanga, I wanted to stand up to say thank you for doing this work. Excuse me, my voice is kind of leaving me. But this work is, I think, super useful because it shines light on hidden parts of the internet that we take for granted. And I disagree with the first person here at the mic who said, if there's been no attack, why do we need to worry about this? I think we need to worry about this because it is a weak link. And I think you're exactly on the right track with that. In terms of figuring out what tests to do here, I think it's completely reasonable to do that design elsewhere. But I think it is important that we do some testing. And I completely agree with the general recommendations that you have. My question to you is, do you have any particular areas in the IETF that could look at this? Or is this something that you have to toss over to the TCD-DB community and hope that they come up with the process? Is there something that the IETF could do here?
Yeah, I think the RFC 6557 that describes the update process could be looked at again, because some of the processes are left at the discretion of the user. And for example, something like using PGP signatures to sign the database is left, the text just mentions that the signature should be used, not must be used. So some of these security measures could be made mandatory, and then the RFC could be looked at. So that is something that IETF can do.
I would encourage you to come talk about it in the relevant working group here.
Thank you.
Thank you.
All right. Thanks for taking some time out of your breaks, guys. Let's thank the presenter one last time. Thanks for sticking around. And if the presenters for the next session want to come and test their laptops and meet their session chair, just come up here.